All right, sorry about that. So what I was going to say is sometimes you'll see probabilities just left as fractions like this, and you should reduce them if you can. Um, or you can write them as a decimal, so 13 into 52, 0.25. So I could just rewrite that as, in this case, is exactly equal to 0.25, so I don't even need to use an approximation, so I could say, right, final answer probability of a spade is 0.25. Oops. All right, moving on. So, assuming an equal chance of having a boy or a girl at birth, what is the probability of having two boys and two girls and two boys in a family of four children? All right, so in this case, you would want to look at your sample space, which is all your possible combinations. So here, the text is just kind of organized it for us. You wouldn't necessarily have to organize it this way, but it helps you keep track of all the possible outcomes. So all four girls, three girls and one boy, and since birth order is something that would matter in this case, there are four different ways to have three girls and one boy, meaning girl, 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 boy is different than boy, girl, 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 right? In the first one, the boy is the youngest, and in the second one, I circled the boy is the oldest, which is why they would be considered different. There are six ways to have two girls and two boys. There are four ways to have one girl and three boys, and there is one way to have all four boys. So that gives us 16 possible outcomes. And the question is asking about what is the probability of having two girls exactly? So we would just count up. Uh, and in this case, that's these six here. And so probability of two girls is 6 out of 16 or 0.0357. So another way to determine probabilities when you don't know um, how many individual outcomes there are is to approximate that. So do it by experimentation. So let's say we didn't know how many possible outcomes there were when we flipped a coin. Now, we do know that there's exactly two heads and tails, but let's say we didn't know and we wanted to know like the probability of getting heads. So one way to approximate that probability would to be actually to flip a coin like 100 times and then count up the number of heads. And however many times you got heads out of 100, let's say it was like 57, you would then assume that that's the probability of getting heads. Um, so we call that the relative frequency method or the empirical method. Empirical just means by experimentation. And so it's the same calculation. It's the number of times A occurred divided by the total number of observations. So in this example, if you're interested in only the number of heads when tossing two coins, and the possible events are zero heads, one head, and two heads, and you could repeat a two coin toss 100 times, and our results are as follows. Zero heads came up 22 times, one head came up 51 times, and two heads came up 27 times. Let's compare the relative frequency probabilities to the theoretical probabilities, and do we have a reason to suspect that the coins are unfair? So the probability of zero heads in our relative frequency model is 22 out of 100. And actually, what we're going to do, because it's relative frequency, we're going to use our approximation symbol. So what did I say? It was 22 out of 100. The probability of getting one head in our little experiment was 51 out of 100. And the probability of getting two heads was 27 out of 100. So how does that compare to their theoretical probabilities? Well, remember, we just did this problem. The only outcomes for flipping two coins are what? Heads, 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 tails, tails, heads, tails, tails. So the true probability of no heads should be that happens once out of 4 outcomes, theoretically. Probability of getting one head, so that happens in those two cases, so 2 out of 4, or 1/2. And then probability of 2 heads is also 1 out of 4. And so we can kind of see how these compare, right? So probability of 0 heads, 22 out of 100, or 0.22. How does that compare to the 1/4? Well, that's 0.25. They're pretty close. And then 51 out of 100 is 0.5. How does that compare to 1/2? Again, pretty close. And then 27 out of 100 is 0.27, and that compares to 0.25. So relative frequency does do a pretty good job as long as you are looking at the long run, meaning you have to flip the coins many times. 100 is a finite amount of times, but it's many times, which is why we're seeing our approximate probabilities come pretty close to our theoretical probabilities, right? All right, moving on. So there are actually 3 approaches to finding probability. So we just talked about theoretical. So that's based on the assumption that the outcomes are all equally likely, and we determine that by dividing the number of ways an event can occur by the total number of possible outcomes. We got relative frequency. We just did that, so that's using experiments to compute the relative frequency of the event of interest. And so that's an approximation of a theoretical probability. And then you have subjective probabilities, and this is something that you do every day to make decisions. So it's just an estimate based on experience or intuition. So it would be like, should I yell at Mr. Toller in the middle of class? How would that benefit me? Well, it would make me feel better, but he would probably get upset and, I don't know, send me to see Miss Clark or whatever. And so in that case, you're doing a little subjective probability calculation in your head based on what your experience tells you the outcome will be. All right. So in this example, we just want to identify the method that resulted in the following statement. So I'm 100% certain that you'll be happy with this car. So it's definitely not a theoretical probability because there's no calculation being made. And for that same reason, the relative frequency or empirical probability wouldn't be right either. This is a subjective probability. This is based on your experience with this car or your experience with people and this car. Based on government data, the chance of dying in an automobile accident during a 1-year period is about 1 in 8,000. So this one is going to be a relative probability or a relative frequency, right? Because this is based on data that the government has collected in a 1-year period, right? So it's based on car accident data, and they're just looking at number of people who died versus the number of accidents and coming up with this relative frequency probability. And then the probability of rolling a 7 with a 12-sided die is 1 in 12. Well, that is going to be theoretical because you're looking at the total number of outcomes, which if there's a 12-sided die, there would be 12 outcomes, and you're looking at the event of interest, which there is 1, 7, and you're calculating a probability that way. All right. So sometimes it's helpful to use something called the complement rule. So not compliment like, hey, nice new shoes. Sorry, I just spelled it the way I didn't want to, the complement rule. And that's the fact that if you know the probability that event occurs, then 1 minus that is the probability that the event doesn't occur. So The probability of a family of 3 children having 1 girl and 2 boys is 0.375. What's the probability of a family of 3 children not having 1 girl and 2 boys? So that's going to be 1 minus the probability of 1 girl, 2 boys, or 1 minus 0.375, which is, oh boy, 0.625. Great. All right, so now we know how to compute different probabilities. We have something that we need to know about called a probability distribution, which represents the probabilities of all possible events. So if you want to make a probability distribution, you're going to make it in a table. Usually you just need 2 rows. You're going to list all possible outcomes, identify outcomes that represent the same event, and determine the probability of each event. And then make a table listing each event and its probability. You know that you've done it correctly if adding up all the probabilities comes out to 1. So here's an example for you. This is a probability distribution for the sum of 2 dice. And so if you have 2 6-sided dice, up here in this table is your sample space. That's your list of all possible outcomes. So again, I've said it a couple times. It's called a sample space when you list all the possible outcomes. So in this case, the distribution I'm interested in is the sum. So I'm going to look at the sum, and I'm going to make a row in my table for that event, the sum. And there's these sums that can be had from rolling 2 dice. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, looking at our sample space, you can see that certain sums come up more often than others. So getting, for example, rolling a sum of 2, there's only one way to do that, and that's to roll what they call snake eyes, a 1 and a 1. But for rolling a 3, there's 2 ways to do that, right? You could roll a 1 and a 2. And I'm using 2 different colored dice to illustrate why these are different. Or you could roll where the blue one's a 2 and the red one's a 1, and that also gets you 3. So there are actually 2 ways to do that. And so after that, you count up the number of times each one of these sums comes up. So there are 3 ways to roll a 4. There are 4 ways to roll a 5. There are 6 ways to roll a 7. You can see we've assigned each sum its own probability. If you add those all together, you do get 1. So we have created the correct probability distribution. This whole table is the probability distribution, okay? Just to be clear. All right. Odds. Odds are the ratio of the probability that a particular event will occur to the probability that it will not occur. So the odds for event A are the probability of A over the probability of not A, and the odds against event A is the reciprocal. So you're just flipping it. Probability of not A over probability of A. In gambling, the term odds on usually means odds against. So what are the odds for getting 2 heads in 2 coins, and what are the odds against it?